I would like to introduce our new device, which is a reference standard series RS3360. It is reference meter combined with a signal generator. This device is dedicated to be a new center, a new heart of our meter test equipment. It can be a central part of our power source, providing generation of 6 independent channels, 6 signals, 3 voltages and 3 currents in case of 3-phase system. So that's the generator, which is generating all those 6 channels by the synthetic approach, generating pure signals by the definition of sine waves and higher harmonics, and it can provide also predefined signal shapes. It can generate also special signals, and it provides also the signals related to power quality. So it can generate also flickers, interharmonics, dips, swells, and all other signals defined by the power quality standards. At the same time, it's the real reference meter, reference standard, which is measuring everything what is generated, all quantities, voltages, currents, power, energies, angles, and of course this is coming with that new features, new measurement of the power quality features, functions, and all those indicators as flickers, interharmonics, and so and so. So this is what is the newest in our product line, and it is becoming a new standard for our power sources, and we can say for the whole ELMA test benches. The device provides a touch screen, so we can control all its functions through this color touch screen. The size is 7-inch, and we can access all functions of the device directly through the touch screen. Of course, we can control device by the remote way from the computer. There's several interfaces available. Currently, we are mostly using the Ethernet and TCP/IP communication to fully control the device. As I mentioned, it has 2 parts inside. That's a measurement, which is the reference meter, and it has also the generator part. So for the purpose of this demonstration, we are going to generate only the voltages, because this example should be dedicated just to present the power quality. So we will be focusing mostly on the voltage side. We will be generating, in this case, 230 volts to all 3 phases. They will be in a symmetrical star connection. It means the angles between voltages 0, 120 and 240. So this is the screen where we can define all values of the voltages, currents, angles between voltage and current in each phase, and also the angles between voltages. We can define the frequency here. We can select here if we want to generate the output values, desired range for both for voltage and for the current, and thus generate. So we can will be controlling it locally through the touch screen. So once signals defined, we can start to generate them. So where in the generator screen, we can switch to the overview. So now we can see that we are generating voltages and angles. And for example, we can check what's the vector diagram here. We have 3 voltages. We can switch off the currents because we are not generating them right now. We can switch to the harmonic view. We can see also free harmonics here in this chart. We can, by a multi-touch, we can nicely zoom it, and we can see the values that currently we are having here. Only the fundamental harmonic. We can have a harmonic list here. Yeah, we can see that we are generating just 100% of fundamental harmonic in this case. Now, once we want to speak about the power quality, so let's focus at first what is the simplest way. It is the harmonics generation. So we can directly, while we are still generating 230 volts, we can directly switch to the shapes. So currently we have here only a pure sine in all three phases, U1, U2, U3. So let's add, for example, additional higher harmonics. Let's set it to fifth harmonic with the amplitude of 10%. So it's enabled. It is showing me how the signal will looks like. We can do the same, for example, to the second phase. We can do the same to the third phase. Yeah. So we having it here for all three phases, and let's go to the home screen of the generator to start to generate, and now switch to the overview. We can go to the load values as well, or we can see the more quantities measured in this screen, and we can see here THDU around 10%. Once we will switch to harmonics and to the chart, we can see, if we will zoom it, that we have on the 10%, now we have a logarithmic scale for the voltages. So we can see that on 100% we have a first harmonic, which is a fundamental, and on 10% of the scale we have a fifth harmonic. Once we will switch to the linear, the graph will change accordingly. So that's the harmonics, and fifth harmonic to all three channels. In the harmonic list, we can see at the same time on the fifth harmonic that we have here the information about 10%. So this is about high harmonics, how we can add them if required. We can go again to the generator, to the shapes, and for example for U1 we can even add another harmonic if required. For example, I can add seventh harmonic with, okay, let's have it 5%. Yeah, we can see the signal. Let's jump again to generate, go to the measurement and the harmonics, and we will see it that 7, we have the 5% here, and in graphical representation we can see it, yeah, that we have a 7% here, just the red color, which is dedicated to the phase L1. So this is about high harmonics, how we can control and how we can apply them by this device. Now let's focus on interharmonics. Now we are not generating any interharmonics, so we can again switch to the generator, to the shapes, and we can try to add to the L1, to voltage in the first phase, also interharmonic. What does mean interharmonic? It means that it's something in between the harmonics. Yeah, so we have first 5 and 7th harmonic right now. So let's play here with it. Let's disable the 7th harmonic, and let's add, for example, 1.5 harmonic. The signal running on 75 Hertz. Yeah, because we're having the fundamental harmonic now, the 50 Hertz. So the 1.5 harmonic will be 75 hertz here. So let's try to generate it. We can set it to the 15%, for example. So let's switch again to the home screen. Okay, we're generating, and let's check the measurement part and the harmonics. Yeah. Now we see that again we are in the red phase, the phase L1 voltage. This is a representation how we can see it from the harmonics point of view, but in case of interharmonics we will be able to see that it is 1.5 harmonic. It's here in the red, so it's somewhere in between. If we will make it, yeah, so we can see this, the 15%. We can check again the scale, yeah, somewhere on about 10% of the fifth harmonic. We have here 1.5 harmonic, interharmonic, and in the list we will see it as a representation between 50 and 100, between the first and the second harmonic, with the amplitude of 15%. And by the theory, it's more complicated about the interharmonics, how they are representing by the multiples of frequencies spread into 5 Hz interval. So it is related to the 16 multiplied by 5, which is 75%, and it is 15% measured here. So this is how we can see also the interharmonics. So we are generating and we are measuring at the same time the interharmonics, and the same or the harmonics are generated also to the phase 2 and 3, but to that phases we are still applying and measuring. To the green and blue phase only the fundamental and the sine wave of fifth harmonic. So this is what we can actually see it. If we switch to L2, for example, we will be focusing only on fifth harmonic and the fundamental. So this is about harmonics and interharmonics. Okay, now let's focus on generating the special signal shapes. They are not exactly defined by the power quality standards, but they are defined by the IECs focusing on electricity meter testing, especially on meter type testing. So when there's a meter type approval, these signal shapes as phase fire or burst fire are coming into the role. So let's focus on that. So again, we are on the shapes page of the signal generator. Let's remove all higher harmonics from all 3 phases, and let's focus only on phase fire, for example. Yeah, so we can directly select this kind of special cut sine wave. This is called phase fired signal, and we can have 3 versions of it depending on which angle the slope appears, on 45, 90 or 135%, or we can define. So let's focus on this in the middle, phase fire 90%. So let's apply the same to all 3 phases. Okay, this is also called odd harmonics, because the result in the frequency view, if we will switch to the harmonics, will be that the signal will consist of odd harmonics. So this is something like a simulation of the signals which can normally occur in the network, in the grids. So let's go to the home apply the signal, and let's go to the measurement, and we can go again to the harmonics view. Yep. And now we can very nicely see that in that harmonics spectrum we can see only the odd harmonics signals, and they are, with increasing the number of harmonics, they are decreasing step by step its amplitude. Yeah, so that therefore it is called odd harmonic, and this is very frequently used effect which occur in the grids, and this is especially these multiples of 3, the odd harmonics which are multiples of 3 are causing a significant problems in the grids. They are summing in the neutral wires, for example, and causing the neutral wires overheating or burning. So therefore it's very important to test meters on these signal shapes, whether the meters are able to correctly measure also under these signals applied, because they can occur so frequently in the grid. So this is a phase fired signal. Similarly, we can focus on the burst fire, so we can change to this kind of signal. Let's switch all 3 phases to the burst fire, which means 2 periods with the signal with the higher amplitude and 2 periods are off. Again, we can generate and we can check how it will appear on the harmonic side. Okay, that's a harmonics view. It will be nicer to see it here. Yeah, so we have 2 periods on and 2 periods off. Yeah, I can return again to generator, and just I will change the phase fire to the phase L1, and let's generate it again and see also this waveform view on the L1. Yeah, that we can nicely see also this signal shape, how it looks like. So those are the special signal shape. Let's focus now on dips and swells. So we'll go to generator dips, and that's a screen here. We can, again, for each channel, we can define, in this case, dips. Dips is when the signal is falling down, which is to be less than a effective value of the signal, effective RMS value, and swell is when it is over the value. So in principle it is the same. So we can set here several parameters where it should start. Now I will select that at a 0 degree. Transition time, it will be in this case minimal, that it will be very sharp. Signal, we can define here what will be the duration of a dips and what will be the depth of that we will go, just for example here, to the 50% of the amplitude of the generated signal, and it will take 1 second, for example. Of course, we can set even the lower value, for example 100 milliseconds. It will be then very short, even shorter. This is possible to make according to the standards, how it is defined. I will select 1 second right now to fall down to the 50% of the amplitude. We can run as much repeats as we need, again defined by the standards, and the period for this effect I'm setting here the 5 seconds, so 1 second we will be off on the 50% of the amplitude, and the remaining 4 seconds we will stay at the nominal value of the generated voltage. So We can have the same to all three phases. Let's start it. And now we can see that that for 1 second it will drop down to the half of the amplitude on all three phases. This is because of the 50% dip, and remaining 4 seconds of the defined repeat or defined period, it is on 100%. We can go also to the power quality menu to discrete events, and we can directly see here those events, and once the new event will come, it will give us a new dip information. So this is how we can see that the dips are generated and measured and correctly recorded. So this is about voltage dips and swells. In this section, let's focus on the flickers. So we need to go again to the generator screen shapes, flicker, and we have here also predefined flicker to U1, for example. We can select the modulation, shape, rectangular or sine, and another parameters here. So let's apply it to all three phases with exactly the same setting. This is as recommended by the standards. Let's go here, start it, and now let's check the measurement to the flicker values. So now it is started to measure the flicker parameters as PST and PLT, and of course this measurement takes a longer time, so therefore we will need to wait at least 10 or 20 minutes while we will be having the measured values. In the meantime, while we are waiting to have a flicker measured, we can switch, and I'll try to show you how nicely we can control this device also from the computer. This is a very simple example how we can interconnect this combined device with the computer through Ethernet cable. This device has its own IP address, so it's very simple to address it, to access it, and to have available information on a bigger screen of the computer. For example, like in this case, we have open at the same time 3 windows, so we do not need to switch or jump between the screens as I did in before when I was focusing on controlling the device locally. So here at the same time we can access the generation of the signals. So one window dedicated, another window here dedicated to showing us the measured all quantities, and of course we can see also the waveforms generated. So and this we can run on any computer, several instances of the visualization software which is coming for free with this device, and it is enabling us to have on one screen several windows available, one dedicated to the generator, another to the reference meter, and having, for example, the tabular data with the highest resolution, and also to go also to the graphical representation of the data. Of course, we can access the menus. All the menus are exactly the same as in case of the device itself, so we can access exactly the same screens as are on the device, but we are on the bigger screen, so we can make those windows much more bigger. We can go to all kind of testing and whatever is available on the device, so we can very nicely control the device on the remote way. So that's quite interesting feature which is coming automatically. So this is something like we having a remote desktop or remote control and display of the device itself. So this is also, I think, something which is worth of mentioning. Of course, when we having the test bench ELMA, it is always controlled by ELMA control software, and ELMA control software is providing all those features. You can define all test sequences, all tests to measure the meter accuracies, verify meter on no load, starting current test, DL test, maximum demand test, and also the latest versions of the ELMA software. We call it a series of ELMA software 18, providing also power quality tests. So you can directly define the tests in the software on the computer to make a flicker verification, dips and spells verifications, harmonics, interharmonics, whatever. So by that way you can fully test in an automatic way the meters or power quality meters. And finally, we can return to the measurement of the flicker and already measured, so we can see the value of PST. Now here it's less than 1, so it's 0.99, so this is what we really expect it to be, slightly below 1, so it's okay right now. We have the value of the flicker in all 3 phases.